It's a great pleasure for me to be here, especially in this festival occasion dedicated to Rush Lion. And I think that the title is very fitting, as was commented before, to his both to the contributions to probability and the spirit of the community which you have fostered. So it's a pleasure to be here. As you know, speakers were asked to say something elegant in probability. I find this very appealing, and for a reason. I mean, we all like elegance, but you see, when I was a youngster just entering the field, actually, you heard two different perspectives of what's of value. So there was the school, which can be summarized by, I think, Paul Federbush's saying that in analysis, analysis is like medicine. If it doesn't hurt or is bitter, then it doesn't do you much good. Then there's another school, I think Barry Simon was trying to hold the flag for that, which is that if you could not present in an elegant way what your proof or what you have to say, it means that you did not really understand it yet. And by nature, I very much wish to be of the latter type, and so it's a pleasure to be invited to talk about things which I regard as elegant. In my work, which was started a long time ago, but actually which seems to be quite a lively topic, as you would see from the reference list even today. One comment, there are many comments about elegance, perhaps I should postpone them till the end, but I heard, to comment on one of them, I heard that in a kibbutz in the north, in Ein Harod, there is an exhibit of Israel as it looked in 1960s, I think. And many people come back from this with a shock because they visit the layout of the houses, how they looked like for those who could afford elegance. And the Scandinavian furniture there of those days somehow does not strike us as it did before. So elegance does depend on taste. It evolves. And actually some of this would be seen in the mathematics that I will be talking about. I will comment on this at the end. Now, the general, one more thing. The subject of my talk combines sort of three perspectives. One, of course, is probability, but then also statistical mechanics and ideas of algorithms inspired by issues of computer science actually also percolate into that. So if any of what I say is not clear, because it's a valid collection of ideas, do not hesitate to interrupt. So to come to the point, I'll be presenting an approach for proving some rigorous non-perturbative results about phase diagram critical behavior in some basic models of probability and statistical mechanics, like percolation and Ising model and slightly beyond. And what I think is what at the time struck me as very elegant about that is that you would see that hard information, like what I say here, it's non-perturbative, it's a regime which cannot be studied through convergent cluster expansions or anything like that. You can obtain non-trivial information about critical behavior there out of mild-looking relations which are summarized as partial differential inequalities. Over here we have an order parameter, a function m of, well, in the statistical mechanics context, it's of the inverse temperature beta n of the applied magnetic field. In percolation context, I will define the corresponding function there. But the main point is it's a function of two parameters, and it satisfies the basic inequalities, the two which together provide you with a very surprisingly potent tool are these two. And I like those, and I'll try to explain what I like about them. Just to let the buzzword out, once we see the derivation of it, you would see that hidden in this. So sorry, I did not finish the previous sentence. What's striking about this inequality is that no parameters diverge here. Just relation between quantities, without any coefficients which go berserk at a phase transition point in both cases. And yet you can, from this, learn something about the location of the phase transition point, the fact that there is no intermediate phase, exponential decay, and so on. This inequality from the derivation, you would see that there is something which is slightly vague to make perfect sense, but actually there is some depth to it. There is something of the flavor of phi cube field theory in percolation, or at least as a bound. And this inequality, somewhat less spectacular in this sense, but actually it's also very beautiful in a way. I will try to explain, because it's a Berger's PDE, a PDI. I is for inequalities. And I'll try to explain where this appears. Now, there are many references which should be mentioned, and I do not have the luxury of just flashing transparency, so I wrote it here, and I would have to erase as we go on. But this technique was introduced in a joint work with David Barsky around 86 or 7. In this case, it was applied to percolation, independent percolation models. Then the same inequalities were derived for Ising systems. Ising models in a joint work with Barsky and Fernandez. Actually, there is a curiously, for Ising models, you get a stronger version. This exponent turns into 2. Then with Barsky, we observed that this inequality, these relations hold for regular unoriented as well as oriented percolation, and as such, it also covers the contact process. We wrote the paper using lattice approximation, so it was the discrete time contact process. So it's percolation plus contact, discrete version. Bezuidenhout and Grimet, I will come to it later, but there was a paper by Bezuidenhout and Grimet extending this to continuum. There was a later work with Paul Zhang trying to do it a bit better, bring it back to this type. I will not go into all the history, but in any case, there are such relations are valid for contact process where the time is continuous, not just discrete. Nick Crawford and Di Maioffe proved such things for show application of this for quantum spin chains, or not just chains, but quantum spin systems. It's not as mysterious as it sounds at first. It's just using a representation where d-dimensional quantum spin system is described as d plus one-dimensional classical statistical mechanics system, and that's why these techniques migrate over there. And finally, I would be remiss if I were not to mention some precursors, in addition to work which I did with Chuck Newman and earlier on Ising systems and phi-4. There was also a very nice intermediate result by Jennifer and Lincoln Chase, and some of what I would say was independently derived by Menshikov. Now, all of that is old stuff but actually, some related works, an extension of this to Q-state Potts model was accomplished. For a while, it seemed to be difficult, as I'll explain. It was accomplished, not of this technique, but of the main result, which I will present in a moment, by Hugo and Vincent. I guess when I say Hugo, outside of this room, people think of Victor, exactly. Over here, you I don't have to correct. And then there is a very recent paper uploaded by the two jointly with Raufi, which is very significant. And I'm glad to say that once I get to discuss this, there will be something new to say, not just review history, hopefully also for the experts in the audience. Now, okay, so that's I need the space. So let's see. I have to make introduction from different directions. So perhaps I should now state what is all that good for. What's the type of result which comes out of this discussion? So a goal which can be reached by the techniques I will discuss is the following theorem for and now a list of models, as you saw. So let's start with independent percolation, and then also Ising, and also some others on any transitive graph. G. There exists a critical point, critical value beta c, which can be infinity. Can be 0 also, such that, well, in case of percolation, let me state it separately. In case of percolation, you get for beta less than beta c that the probability that the connected cluster of the origin, let's see, the connected cluster which includes the origin, probability that this contains more than n points, decays exponentially, so it's bounded by e to the minus mu, which depends on beta. Let me not write it all, times n. Whereas for beta larger than beta c, the probability that the origin percolates to infinity, so that the connected cluster is infinite, is actually positive. So there is a sharp transition from it's a sharp transition from a behavior which can be easily shown by all kinds of expansions and simple estimate, kind of exponential decay. Oh, beta here, think of it as the density of the bond percolation model, for example. It's actually the result is actually more general. Let's see, if this is a graph, we saw more interesting transitive or almost transitive graphs drawn here, but that's the fastest to draw, so let me just draw this one. Bond percolation model is one where actually you are not restricting the edges to nearest neighbor. Any 2 points can be connected by an edge, and the probability that an edge, the edge variable, say omega e, which is 1 if the edge is connecting 0 otherwise, the probability that this is 1, for the more general formulation, let's write it as 1 minus e to the minus beta j. This is a sort of poor man's way to say that this depends on je. This is proportional to a control parameter beta, which we would be varying, times some fixed rate je, which can contain some structure. So it may be nearest neighbor, or it may be decaying at a certain rate, and so on. So it's convenient to have one parameter to play with, and that's this beta. And of course, the probability has to be bounded by 1, so that's why the function is written this way. Okay, it's a standard trick which enables to generate models with long range mixed with. Okay, then that was for percolation. For Ising models, there is an analogous transition, and that is beta less than beta c. The spin correlation sigma x sigma y decays exponentially with positive constant. Oh, this is now restricted to models where the couplings j themselves are exponentially decaying, because if not, then of course there will be direct coupling, which is so that's assuming j is exponentially decaying. Whereas for beta large and beta c, let's see, the magnetization, the mean value of the spin in the limit in which you have taken the infinite volume limit first, and then take h down to, let's see, I guess one way to do it is either positive boundary conditions or take H to 0 of the magnetization at inverse temperature beta, magnetic field H. This is actually non-zero, is equal to some function of beta, which is positive. And furthermore, so sorry, it takes a while to write it, and most of you know what I'm talking about. It is the concepts, but if for some it's not clear, please ask. Furthermore, well, let me not write all the words, but draw a picture. And let me draw the picture first for Ising model. So the phase diagram of the system. Oh, should I introduce the Ising model? It's customary to ask if I see experts saying no. Okay, and others are intimidated, so the no's have it. Okay, so we have a magnetic field and inverse temperature beta. The assertion is that there is a critical point beta c, and let's see. Oh, I guess the red color is not visible, so I would not do that. But now, if there is a critical point, it means what you can also derive from these inequalities is that are statements about what happens as this point is approached. So, as I started to say, for beta small, at this corner of the phase diagram, it's easy to see that you have exponential decay. It's like percolation model with very weak collection of very weak intensity. In such percolation models, the typical configuration looks as collection of clusters which are seldom very large, and the probability of observing long connection is exponentially small. Whereas where the density increases, an infinite cluster occurs. The analog of that for Ising model is, again, decay of correlations and transition to this. I guess what I wanted to say better than that is that sigma x, sigma y at h equals 0 is bounded below by m square beta, which is a positive number. Somehow it slipped on my mind. Instead of this, I could have written that. And that now, of course, the analog of this for percolation is probability of connection between two sites. It does not decay. There is that's referred to as the long-range order. What you can also learn is that that m, by this theorem, from this point on, m starts non-zero, and you can say that along this line, m as function of beta is greater or equal than some constant beta minus beta c to power 1/2. Actually, for Ising model, you can get even better power due to what I mentioned here. But let me leave the phase diagram. Let me leave statements which are true for both models. As function of magnetic field for the quantity m along this line at beta c, but function of h is greater or equal than constant times h to power. Let's see. Sorry, that's a mistake. For okay, let me write like this. It's 1 for percolation here, 2 for Ising model, and this quantity goes as 1/2 for percolation, and it's more singular. It's as 1/3 for Ising model. Okay, and on the other hand, as you approach the critical point, from this direction, the susceptibility chi, which I will define in a minute, diverges is bounded below by constant times beta c minus beta to power 1. Another way to summarize this is to say that we also learned something about the critical exponents, which are the powers by which this quantity is expected to behave. And curiously, the bounds essentially say, these inequalities imply that you have mean field bounds for these exponents for any transitive graph.
So for Ising model, H is a magnetization. What's it for percolation?
Thank you for asking. So the next thing is exactly this question: what's the analog of how to relate these results for Ising model to percolation? Where in percolation model you have a graph. Edges are inserted independently initially. Say now what's a spontaneous analog of spontaneous magnetization? It turns out that a good analog for that, let's see, is defined as follows. I already said what is the beta for percolation. So now let's define. M would be essentially. Well, no, sorry. Yeah, I'm just defining it. M beta H would be the expected value of 1 minus e to the minus h times the size of the connected cluster of the origin. To make it more palatable, or intuitive, sorry, think in terms of let's see, one way to think about long-range order is to well, it relates to a device which Bob Griffiths has introduced. Add extraneous site here. We refer to it as ghost usually, or Griffiths ghost site, and consider a model in which you also establish direct links. This site is linked by edges to all other sites, except that the probability of these edges to be occupied is independent with intensity h. Okay, so another way to put it, and I'm using this in analysis, is to say the following: take your lattice and sprinkle kind of a Poisson distribution, well, discrete distribution of points with density h independently, and then this is precisely the probability. The density. Yeah, the density. The density is not h but h tilde, which is 1 minus e to the minus h. H tilde is the probability of a point landing. The probability that no point lands on a connected cluster is this. Right? If you have a cluster of size c, the probability that no point is there is the number which we have raised to the size of the cluster. So this is essentially the probability that the origin in our hybrid system, it's the probability that. It's the probability that there's no need for that. The probability that the origin is connected to the ghost. Okay, and now what you can see immediately is that this probability depends on two quantities. One is the two sets of randomness. One is the structure of the bond of the percolation configuration. The other is this random sprinkling. Now, as h tends to 0, the probability of there being kind of a marked point on the connected cluster of the origin tends to 0, no matter what the size is, as long as it's finite. If the size is infinite, then with probability 1, it would get marked. So this quantity converges when h is taken down to 0 to precisely the probability that the connected cluster of the origin is infinite. And another quantity which is of interest is the derivative of that with respect to h, and it behaves like the magnetic susceptibility that you just differentiate, and there's no problem differentiating. This is a monotone functions of h. So this is exactly the expected value of the connected cluster of the origin, which is actually equal to sum over lattice sites of the probability that the origin is connected to x. So x are vertices of the graph. It doesn't have to be lattice, but vertices to the graph. So that quantity is the analog of the magnetic susceptibility, which for Ising models is sum of the percorrelation function. once you introduce this terminology, suddenly the two systems start to talk to each other. And historically, when we were developing our insight on that, it was actually extremely helpful to think in parallel about the two models, because certain things are elementary in the context of Ising systems. You simply differentiate the Gibbs measure. Yet other things are very transparent in the context of percolation. So you kind of see what can be done here and ask yourself, what's the analog of this there? And it was climbing on your 2 feet, some kind of pair of ladders. It worked beautifully. And of course, there is a one-parameter family of the Fortuyn-Castellane Q-state Potts models, within which these two models are embedded as special cases, Q equal 2 and Q equal 1. Okay, how am I doing? I almost wasted all the time. Not yet. Okay, so that's the goal, and that's the theorem which follows from it. And now I want to discuss two natural questions. One is, how do you get from here there, and where is this coming from? So in a way, the probability discussion and the algorithmic component of the discussion is at this part of how do you prove those inequalities. That's in a way the heart of what would be natural for this meeting. But when we introduced this, ever since it was introduced, I had the feeling that this other part of how do you go from here to these results, that was, and probabilists have really tried to escape from that. And they certainly do not regard this as elegant or what. And I think it is. So I would like to spend some time discussing the PDE or PDI question of what good are these kind of inequalities and why you can think of them as actually your friends and rather elegant beasts rather than some horrendous stuff that you escaped from to probability. I got the feeling that various probabilists are in the field because they did not want to do PDE.
These inequalities both hold simultaneously.
Yes, yes. So this inequality is for the function m, which is a function of beta and h. And the function is monotone in a natural way. You know, the m is the monotonicity is quite familiar to that. So okay, so how do you see the light from that? I will have to erase this, but at least keep this picture. So for an intuitive grasp of I would now present a heuristic description. So proceed heuristically. And it's not terribly difficult to build an argument which is totally solid based on these heuristics. But proceeding heuristically, you could say, look, we kind of know what's happening here at the far corners of that. Namely, in this regime, m is analytic as function of h. Analyticity breaks down at a point. Beyond that, I skipped a point. In fact, what I was just starting. Before the heuristics, sorry for the disorganization. Beyond the heuristics, I want to introduce a very useful perspective which would link with Burgess. So it's the shock shock formation perspective. So actually, there are three things which I wanted to still talk about. One is this: the shock, the perspective of phase transition as a formation of shock. Now, how does this work? Remember what m is, and in case of, let's see, what is it? M is defined here. In case of Ising model, it's the spontaneous magnetization. It's the function which is analytic except along this line from beta c up. So that's what you expect it to be. So ask yourself, how should the profile of this function, as function of h, evolve as you move this line. Physically, it corresponds to the question of how does the profile of the magnetization at beta h, so m of h, how does the magnetization look like at given beta? Now, at high temperature, at beta equals 0, the spins do not talk to each other. The expected value of the magnetization is single side calculation, which is trivial. The answer is hyperbolic tangent of beta, elementary exercise. So that's at m at beta equals 0 and h. It's just a hyperbolic tangent of h. I include the magnetic field factor in the magnetic field, the beta factor in h. So it's hyperbolic tangent of beta h. It's just at beta equals 0, the spins do not interact. And this is just a single side calculation. Now, when you have spontaneous magnetization, the function has a discontinuity, actually. A discontinuity forms here. Because the limiting value of m when h tends to 0 at given temperature is actually non-zero. So the question is, how do we get from this to that? How does this profile evolve? And what you expect to see is that, just on basic intuition of the physics of it, is that there is a critical point at which, this function gets pushed here, and then there is a critical point at which it comes with an infinite slope without discontinuity. And if you further lower the temperature, a discontinuity builds up. So this is essentially evolution of a profile of a function in which a shock discontinuity emerges. Now, emergence of shock solutions is the sort of bread and butter of hydrodynamics and applied mathematics and so on. The very simplest example of a function which leads to shock solution is Berger's equation. And it links very intimately with that. So Berger's equation is, again, sorry for talking about the subject some of you have been trying to avoid, so did I for a long time. In hydrodynamics, this kind of situation enters where when you have a velocity, say, take one-dimensional system. Suppose at each point there is a well-defined velocity of a fluid, an incompressible fluid. So incompressible, yes. V of x. Just a second, I have to. Yeah. No, sorry, it would be compressible. But you have a velocity. Sorry, you have a velocity at site x. And there is a certain profile. Let me draw the profile differently like that, say. And then consider a situation where the time derivative of velocity at site x and t is equal to v x t times partial v with respect to x. This describes the very intuitive situation in which particles move with the velocity of the place where they are. And if they just keep moving at this constant velocity, then essentially the graph of the function evolves in a very simply integrable way. You start from the initial graph and then move each point let xt be equal to the initial point, x naught, plus t times the velocity of x naught t. At the initial point, initial time. And in this basic physics picture where particles just move with the velocity they have initially, the profile of the velocity as function of x evolves in a very simple way, that the graph, you can reproduce the graph by just pushing points at a rate which is proportional to the height. And then you see immediately that shocks will form. The reason is that if this point moves faster than, say, this, where it's just stationary, or even faster than that, at some point it's going to overtake it. So at some point, this is going to reach 0, and in the meantime, all kinds of other things could have happened, but with a bit of convexity type assumption, actually, the shock, you can easily see that under certain conditions which cover this one, there will be no shocks except at this point, the first place where it occurs. But the fact that shocks happen is immediate consequence of this. There is one way in which this could be avoided, and that's if you have viscosity. So there's a coefficient d times second derivative of v with respect to x. That's related to diffusion. So particles, in addition to just drifting, they diffuse. And in that situation, the shock does not build up. Now, what do you know? Chuck Newman made the observation way back that the magnetization profile of an Ising model actually obeys exactly this equation when you translate m to v, beta to so m becomes velocity, beta is time, and h is position. Not only this, but in the mean field model, there is a viscosity term, which is d equal 1 over n squared, where n is the size of the system, which makes it's a beautiful realization that you do not have phase transitions in a mean field model, finite and mean field model, just as you do not have shock formation in there. Now, what we have here is exactly the inequality. In other words, there the statement would be without viscosity, this is equal to 0. Oh, sorry. I think there is a difference in sign between this and that, but up to sign, well, no, perhaps it's correct. Yes, there's a sign difference between v and x and h and x. But basically, this construction can be applied to this magnetization profile that we discussed here. The only thing is that you do not have, in general, an equality. You have inequality. So that's why I refer to this as the Berger's partial differential inequality. Okay. Now, let's see. That's to explain the term Berger and to point out this remarkable fact that this has some legs. It didn't come from nowhere. Okay, how to apply this? Remind me, please. We have how much? 8 minutes. Okay, so oh gosh. So a quick analysis, quick and dirty, but it actually shows you something spectacular also. How to use these inequalities. So let us consider this function along the real line when h is equal to 0. That's where the interesting action is. It's very natural to assume that when m tends to 0, it vanishes, and even when it goes singular, m for h small, you may expect that m of beta and h would behave as some amplitude a times h to, as constant times h to a power. Let's call it a of beta. Now, let us combine the inequalities 1 and 2. They tell you that m is less or equal than h dm dh plus, I'm now substituting this in here, so I get, there's a factor missing j, but it's harmless, so it's some fixed j times m baribua dm dh, and there is another term m squared, which is lower order, and it really doesn't affect the analysis, so let me ignore it at this point. Now pay attention. When you have this inequality, and if you did not understand, if you disengage from what I said so far, that may be a good time to wake up, because it's an interesting situation. When you look at this differential operator, h ddh, when applied to functions of this kind, it essentially multiplies m by a constant, which is exactly the power. When you differentiate and multiply back, you just pick a coefficient, which is this power. So along the line, up to the point where something would start to go berserk, this inequality is trivially satisfied, because m, being an analytic function or just differentiable function, has a first order approximation here. So along this line, a is equal to 1, and then this essentially says that m is less or equal than m plus some stuff, and everybody's happy that there is no further information contained here. However, what would happen when you reach the critical point where this behaves with a if A is less than 1, what you obtain here is smaller than that. And then the inequality holds not because this term is there, but this doesn't really compensate for much of this. It's this term which kicks in. And when you obtain inequality that some multiple 1 minus a, whatever it is, times m is less or equal than jm squared dm dh, you can cancel one factor of m, and what you learn is that certain constant is bounded by the derivative of m squared with respect to h, from which you immediately read that m squared, as you move along this line, is greater or equal up to constant than h, which tells you that m itself is bounded below by h to power 1/2, which says that as far as the possible values of a go, a can be 1, no problem there. But if it's not 1, it has to be less or equal than 1/2. There's a forbidden gap in the range of values which this exponent can take. And then when you feed this up here, you find another forbidden gap for the exponent, which, I mean, when you put it here, in fact, I can just do it immediately. If this takes care of only half of that, not more, then this has to compensate, which tells you that dm d beta is positive. So that's the intuition behind it. So this is very, very beautiful. Now, in the remaining 4 minutes or 5? 3 minutes, I would like to describe how to prove this. Where does the proof come from? And that also relates to the question of what's elegant. There was an argument which we devised, and we were very pleased. We thought of it as an elegant argument, but then we ran into a problem. So the proof is basically, let me give the percolation version of it. The probability, m, which is the probability that the origin is connected to one of those green sparkled points. I wish I had green and you could see it, but these are kind of randomly sparkled points. This event can occur in a number of ways. First of all, it could be that along the connected cluster of the origin there exists precisely one green site. So this is equal to, let me break it. One possibility is that there exists a unique green site to which the origin is connected, and then there's a cluster. So sorry, I should draw it like that. There is the origin. There is a green site that it's connected to, and there is a boundary across which there are no edges. There's a unique site that it's connected to. Then, if there is more than one site that it's connected to, we split it into two cases. One is that there are two disjoint paths which end at disjoint at these different points. Or there may not be such point, in which case there will be choke sites. And you have the following situation, that there exists some cluster. I mean, there's a sequence of choke points, but behind the last one, that site is doubly connected by this joint pair of sites, and this has to be connected. Now, this event, if you look into the guts of it, you see is exactly h dm dh, kind of Russo formula that supposedly you're familiar with. This term, that's a difficult one. We heard about conditioning in the talk of Stas yesterday, but we are not in 2 dimensions, so it's very difficult to condition on what's the first crossing and where do you find the second. Luckily for us, we had the Vandenberg Kesten inequality, which says that probability of disjoint occurrence of two events is bounded by probability of product of probabilities. So this gives us m squared. And then as far as this is concerned, by conditioning on this, you see that, again, you get the Vandenberg-Kesten bound for this. That peels off, that gives you magnetization in the depleted lattice. So that's where the inequality comes from. M, and then when you peel one of these factors, this is exactly the m d beta. Because this is the event that the site is pivot. Once you peeled off this condition, replace it by a factor, it's exactly the statement that this is pivotal. And that's the proof. I thought it's elegant. Problems. The Vandenberg-Kesten inequality is a bit problematic as when you get beyond the independent percolation. So for Ising systems, we found a similar statement, except for Ising systems, those who know the random current technique know that random currents have no sources. So whenever there is such a vertex, there has to be another line dangling here. Which means that actually, in case of Ising models, instead of 1, you can even say you can get factor of 2 here. But using random current technology, this could be done. When I met Hugo and Vincent, I expressed my frustration that in the Q-state Potts models, we have an inequality which works for Q equal 1, same inequality, but only better works for Q equal 2. No complicated coefficients here, just this basic logic. What about different values of Q? So they have done two things with this. One is they came up with a different proof for these two cases, essentially by showing not that as you come from this beyond the critical point you are here, but rather when you come from this side you're there. But I was a bit sorry to see this argument because they were tossing out the beauty of that, replacing it by some intricate result. But we remained friends. And then, but then more recently, they uploaded this joint work which I mentioned, in which the general Q-state Potts model, part of the result, the essential part of it, not all the critical exponents, but the absence of an intermediate phase, was proven using deterministic, using decision tree method. And then a funny thing happened. I remembered that actually in my youth, before we had the Kesten-Vandenberg, in the paper with Chuck Newman, we, to prove that exponential decay of two-point function implies all the other things that I said, that the probability of the cluster to be of size and also decays exponentially, we used a statement which says that the probability that endpoints are connected, so let me start with probability that 3 points are connected, is less or equal than sum of the product of two-point functions. This is generalized to endpoints in terms of sum over trees. How do you prove that? Well, we realized that had there been, at that point, Vandenberg-Kesten still did not exist, but so we used an algorithmic construction to prove that. I would skip this now because there is no time, but we used an algorithm which apparently was earlier used by Shamir. I think it's Eli Shamir, Jerusalem, and company, to explore numerically connected clusters. And using the algorithm, we could actually prove exactly what we wanted. Later came the Kesten-Vandenberg, which produced what we thought would be a more elegant proof. The Vandenberg-Kesten proof of inequality proof of that says if all are connected, then there has to be a point which is disjointly connected to the 3. That's elementary observation. And then the Vandenberg-Kesten inequality does this. So for a long time, we thought, this algorithm took a bit of time, but that's how you should do it. But now I remember this, and I realized that actually you can prove things without Vandenberg-Kesten if you just use this algorithmic exploration method. So actually I went back to this inequality, and what do you know? There's a very elementary proof which I wanted to present because that's the probability part, but I will not do that. There's a very elementary proof of this very inequality using not the new extension, but the good old, another really very elegant statement by, what is it? The D S cubed. You guys know it. One of the S is Schramm. Louder, please.
O'Donnell, Cervedio, Schramm, and
Sachs, exactly. So they essentially, the remarkable statement which they formulated combined with a very elementary exploration technique similar to what we did, leads to a proof of this inequality. So it's the kind of proof that which at one point I would regard as less elegant because it's algorithmic, complicated, and so on. But actually, ipso facto, it looks much nicer. And it works now that our friends have. So in the paper, which was uploaded recently, Hugo, Vincent, and Rofi have done two things. One is that, and I think that we are going to hear about it tomorrow. One is a generalization of this to monotone measures. And then they invented another algorithm which bypasses this beautiful inequality for proof of absence of an intermediate phase. So what I woke up to the fact is that this general result, which you have, it generalizes this to monotone measures, suffices, and it keeps this beautiful argument still alive. So thank you, Hugo and Vincent.